All right then, now let's see the question number 7. And it is something like this. Two equal resistances. All right, so that's going to be a very important clue word. It's equal, okay? When connected in series to a battery, consume electric power of 60 watt. That's fine. And if the same very resistances are now connected in parallel and to the same battery, so the battery is same, just the connection has been changed from series to parallel, we need to calculate the electric power consumed. Well, this is a very, very straightforward. Nothing can be so straightforward as this question. So it's something like, say, initially 60 watt, so that's V square divided by 2R. And later on, we need to calculate the actual power when they are connected in parallel. So R and R in parallel is going to be R by 2. So straightforward, this P is going to be 4 times as much as the power consumed in case number 1. So the correct option will be option number 4, which is the correct one for question number 7. Let's move to question number 8. The 8th question that has been extracted from electric charges and field under the chapter electrostatics. So the question is something like this. 3 charges, that's capital Q and 2 small q each, are placed at the vertices of a right angle isosceles triangle as shown in the figure. So here's a right angle isosceles triangle, and in this given case you could see the placement of the charges. And we need to calculate the electrostatic energy of the configuration. It is given to be 0, and for that given situation, what is the value of capital Q? In other words, what should be the value of capital Q for which the electrostatic energy of the configuration, mind you, it's not the energy of one charge. Okay, so the configuration is the unique interaction between 2 pairs from the given system, isn't it? So if I call them as 1, 2, 3, the unique interaction would be 1, 2, 1, 3 and 2, 3. So let me write, and here, yes, so in order to write that, let me say this is A, this has to be root 2 times A because of the given credential. So the energy would be, the total energy is KQQ by root 2 times A. So let's go clockwise, 1, 2, 3. So this is 1, 2. Then let's go with 1, 3. So that's plus KQQ divided by A. And then the third one and the final one is 2, 3. And that 2, 3 is going to be plus KQ square divided by A. All right, so we have written the electrostatic energy of this given configuration. And the question wants the value of capital Q so that the total energy of interaction has to be 0. So I need to equate it to 0, and you do that. That's a small level of calculation. You equate to 0. For question number 8, you would get first option as the correct option. Fine then, it's time to move to the 9th question. Question number 9, the Wheatstone bridge circuit from the chapter current electricity. Let's see, and it's a very, very straightforward question, believe me. In a Wheatstone bridge, the figure is there. Resistance P and Q are approximately equal. So P and Q are given approximately equal. When resistance R equals to 400 ohm, the bridge is balanced. All right, so here, when this is equal to 400 ohm, the bridge is balanced. So let's see, what does it say? It says something like this. P by 400, this is 400, equals to Q by X, that's a first fact. On interchanging P and Q, so now this becomes Q and this becomes P. The value of R for balance is 405 ohm. So we need to calculate the value of X is very close to a slight bit of approximation we need to put given the fact the resistances are almost equal. So here now in the second situation I get Q upon 405, because this is Q, this is 405, would be equals to P upon X. So now these are the two equations, and you can solve with the given condition that the value of P is almost equals to Q. You put that only while solving at the last part. You put that approximation, fine. You solve it and the option would be very close to option number 3, which goes out to be the correct option for question number 9. Time to proceed to question number 10.